Hello everyone and very warm welcome to Chemical Engineering Insights, the podcast where we deep dive into the fascinating world of chemical engineering. I'm Akansha.
And I am Chandu. Today we are tackling a crucial topic in reaction engineering and heat source. Chemical, chemical heat source in fixed bed reactors. This is a fundamental concept with significant implications in designing and operating and industrial chemical processes.
We'll be dissecting the principles behind heat generation and dissipation within these reactors, drawing upon some insightful material we've been studying. This topic will apply the approach of transport phenomena and the approach of shell energy balance. The system would be that there will be a heat production or heat consumption because of chemical reaction. Both cases can be there, either endothermic or exothermic.
Actually, there are many kinds of systems. That is, there may be mixed flow reactor, CSTR, or fluidized bed reactor. But we are considering only a type of reactor, that is tubular reactor, which is fixed bed plug flow reactor. Here we are considering plug flow reactor because there is no change in radial direction. The change will be in Z direction, which is the axial direction of the fixed bed reactor.
So there are three zones in our fixed bed reactor, which is Zone 1 consists of non-catalytic spheres and Zone 3 consists of no catalytic spheres, whereas Zone 2 consists of catalytic spheres. This is the zone where actual chemical reaction is taking place. In Zone 1, we are considering it from a length of minus infinity to 0, and Zone 2 varies from z is equal to 0 to L, and Zone 3 varies from length z is equal to L to plus infinity. So this is similar to a fixed bed reactor with packings like a distillation column or absorber.
Here we consider a tubular reactor of radius r. Tubular reactor is obviously a cylindrical. So here we will use a cylindrical coordinate system. Here one is r direction r. Here one is in r coordinate along radius, and another is z along with length, and third is theta. Here it will be used in special case, but here in this case we are not considering it. We only consider r and z coordinate system. When we talk about fixed bed reactor, we will get a term called superficial velocity, where velocity depends on area. Here superficial velocity is determined with the term v0, and this is a different from actual velocity. Fixed bed contains particles. This superficial velocity means velocity into the reactor without considering the particles. Okay, Akansha, can you tell me what is the object of this video?
Yes, the objective of this topic is to study the steady state actual temperature distribution in the fixed bed reactor. So we are considering only variation only in the actual direction. And we are considering steady state. In steady state, our accumulation is 0 because steady state refers to there is no change in no change in any property with respect to time. So there is no accumulation. And here we have the chemical reaction can be both exothermic or endothermic. If it is exothermic, there will be increase in the temperature, or if it's endothermic, there will be decrease in temperature. So our main objective is to generate a mathematical model.
Okay, then can you tell me how to approach for the temperature distribution?
Since we have a tubular fixed bed reactor, for this to calculate the temperature distribution, we will be making a shell energy balance over tubular fixed bed reactor.
Now select a disk of radius r and thickness delta z in the catalyst zone. Now we will do energy balance for this. Here we are using E, which is a combined energy flux term vector, which is a combined energy flux vector. Because it is a flow system, when we do balance on a flow system, then convective, molecular and convective fluxes may be involved, so we will use a combined energy flux also.
The shell energy balance equation is as follows. Rate of energy in by convective transport minus rate of energy out by convective transport plus rate of energy by molecular transport minus rate of energy out by molecular transport plus rate of work done on the system by molecular transport minus rate of work done by the system by molecular transport plus rate of work done on the system by external forces plus rate of energy production is equal to 0. Here we consider combined energy flux, which is a result of convective as well as molecular transport, and the rate of work done on the system and by the system is 0. Hence, because there are no forces acting on the system and there is no work done on the system by external forces, so we consider that term to be 0.
So after cancelling some terms, we will left with three equations like rate of combined energy flux in minus rate of combined energy flux out plus rate of energy production. Here each term described as like this. pi r square Ez at z minus pi r square Ez at z plus delta z plus pi r square delta z into S equals to 0.
Chandu, why do we use SC here?
Here SC is volumetric rate of thermal energy production by chemical reaction. SC in general a complicated function of a pressure, temperature, composition and catalyst activity. So for simplicity, here in this we represent SC as a function of temperature only. Here that equation can be represented as SC equals to SC1 f of theta, where theta is a function of temperature, theta equals to T minus T naught by T1 minus T naught, where T is local temperature in the catalyst bed, SC1 and T naught are empirical constants for the given reactor inlet conditions. Here capital T variable is a variable that T is varying with Z. That means that T is varying in zone 2 in axial direction only. Okay Akanksha, now we got the cell energy balance equation. Can you explain me how we got the terms of that equation?
Yes, Chandu. Here we are multiplying pi r square with the flux because flux is nothing but quantity per unit area per unit time. So if we multiply it with area, which is cross-sectional area here, cross-sectional area of the tube is pi r square. So we get pi r square into Ez will give us the rate of energy. So we are considering rate of energy in minus rate of energy out, plus we have SC is nothing but volumetric rate of heat generation, right? So if we multiply it with volume, we will be getting rate of energy. So all the terms are in the same dimensions. Chandu, why do we use combined energy flux in shell energy balance equation?
Because we are considering a flow system. In a flow system, when we do balance, that involves convective flux, molecular flux and conduction flux. So we combine all these fluxes as a combined energy flux. So we are using term Ez. Okay Akanksha, here in cell energy balance, we are using only in Z direction. Can you explain me why we are considering only Z direction?
Yes, because in a plug flow reactor, we assume that there is symmetry around theta. Since there are no changes in theta direction, we are considering it to be 0. And then in radial direction, since it's a plug flow reactor, there are no changes in Z direction, sorry, R direction. And there is only one dimension left, that is Z, and in plug flow reactor, changes only happen in axial direction.
Now we have the cell energy balance equation. Can you now explain me how to proceed now?
Yes, Chandu. So here we had pi r square Ez at Z minus pi r square Ez at Z plus delta Z plus pi r square into delta R into SC is equal to 0. To simplify this equation, we will divide the whole equation by pi r square delta R. And then we get an equation like Ez at Z by delta Z minus Ez at Z plus delta Z by delta Z plus SC is equal to 0. And then we are multiplying the whole equation by minus 1. Now we get Ez at Z plus delta Z minus Ez at Z divided by delta Z minus SC to be 0. Delta tending to 0, we have Ez at Z plus delta Z minus Ez at Z divided by delta Z to be equal to dEz upon dZ. Now we have the simplified equation as dEz upon dZ is equal to SC.
Okay Akanksha, here I want to give you a note. This operation is not legal since we are not dealing with a container, but rather with a granular structure. So we just assume system as a continuous. So here we can use that limit as the delta Z tends to 0, and we are dividing the whole equation with pi r square delta Z. Nevertheless, we perform this limiting process with understanding that the resulting equation describes not point values but rather average values of Ez and SC. In the equation dEz by dZ equals to SC signifies combined heat flux per unit length is equals to volumetric heat generation. Here we are getting Ez equation. Now we substitute Ez in dEz by dZ equals to SC equation. We are getting this equation. Here Qz is the energy conduction in Z direction. Here we are using Fourier's law, and the equation is Qz equals to minus K effective at Zz dt by dz. Here I want to specify one thing. Here we are using K effective. Why only effective? Because if we take at any point in Z, there we get a catalyst, reactant, product. Here K represents all materials, all components combined value. So we are using the term K effective. And tau Zz is a shear stress in Z component in Z direction. And here we use Newton's law of viscosity, where the equation is tau zz equals to minus 2 mu Vz into dVz by dz, and each term is an enthalpy. After substituting all these terms in the equation, Akanksha, can you explain me how to simplify this equation?
Yes, Chandu. Here we have many terms. In this, when we take the first term, we are considering variation of velocity z in z direction. Since it is a plug flow reactor, there is no change of velocity in z direction. There is change only in r direction. So we consider this term to be 0. And then in the second term, we have variations in both temperature as well as velocity. So when we split these terms, we have two terms in which in one of the term we have dVz upon dz, so that is 0, but the second term is rho Cp V into T minus T naught. So here we are considering only the change in temperature with respect to z. So we have this equation, this is non-zero, and then for the next term again Vz is not changing with z, so this term is also 0, and the next term also corresponds to Vz is not changing with z, and the next term we have dVz upon dou z, and then this is also not changing, hence this is also 0, and then we have k effective dou T upon dou z. Since temperature is changing along the axial direction, this term is non-zero and Sc is non-zero. Welcome to this in-depth exploration of combined energy flux equation. In this realm of fluid mechanics and heat transfer, understanding how energy is transported within a moving fluid is crucial for analyzing and designing various engineering systems. Today, we will dissect the concept of combined energy flux, drawing directly from the principles outlined in our sources. This session aims to provide a comprehensive understanding of different mechanisms contributing to this flux and how they are mathematically represented. When dealing with fluids in motion, energy isn't just stationary. It's being carried and transferred through various means. We need a way to quantify the total energy being transported across a given area, and that's where the concept of combined energy flux comes into play. This combined energy flux accounts for different ways energy can move with and through the fluid. Several key mechanisms of energy transport in a fluid are described. Firstly, the convective transport of energy, which is energy carried by bulk motion of the fluid itself. Imagine there is a river carrying not just water but also thermal energy within that water. That's a basic analogy for convective transport. Secondly, energy can be transferred at molecular level through work associated with these molecular motions. This relates to the stresses within the fluid and the work done by these stresses as the fluid moves and deforms. Think of friction between layers of a moving fluid generating heat. This is linked to the work done at the molecular level. Finally, there's conductive flux, also known as molecular flux, which represents the transfer of energy due to random motion and interaction of molecules, typically driven by temperature gradients. This is what we commonly understand as heat conduction. The combined energy flux vector, often denoted by E, elegantly combines these different modes of energy transport into a single expression. Our goal today is to break down this vector into its constituent parts, understand the physical meaning of each term, and appreciate its significance in the broader context of energy balance in fluid systems. Now let's discuss about convective energy flux. Let's begin by examining convective transport of energy. We know that fluid has a velocity v, volumetric flow rate across the surface element ds, which is perpendicular to x-axis, is given by vx into ds, where vx is the x component of fluid velocity. This makes intuitive sense. The faster the fluid moves in the x direction, or the larger the area, the greater the volume of the fluid crossing that surface per unit time. Now, this moving fluid carries energy with it. This energy comprises both the kinetic energy per unit volume and the internal energy per unit volume of the fluid. Kinetic energy, as we know, is the energy of motion, and internal energy is the energy stored within the molecules of the fluid due to their temperature and intermolecular forces. The rate at which this total energy is being swept across the same surface element ds perpendicular to the x-axis is then the product of energy per unit volume and the volume rate of flow. Similarly, we can consider surfaces perpendicular to the y and z directions involving the vy and vz components of the velocity respectively. From these considerations, we derive the concept of convective energy flux. This is the rate at which energy is convected across a unit area. The components of convective energy flux in the x, y, and z directions are given conceptually. More formally, the convective energy flux vector can be represented as rho into u plus half v square plus p into v, where rho is the density, u is the internal energy per unit mass, and half v square is the kinetic energy per unit mass, p is the pressure, and v is the velocity vector. While the term PV represents the rate at which work is done by pressure forces in moving the fluid across the control surface, and it's naturally associated with the convective transport. To solidify this, imagine air moving through a ventilation duct. The faster the air moves, the more air molecules cross a given cross section of the duct per second. Each of these molecules carries with it a certain amount of internal energy related to its temperature and kinetic energy due to its motion. The total rate at which this energy is transported across the duct's cross section due to the bulk motion of the air is the convective energy flux. Next, let's delve into the work associated with molecular motions. We are considering a force F acting over a distance dx, resulting in the work done dw is equal to F into dx. The rate at which this work is done, or the power, is then dw by dt is equal to F into dx by dt, which is equal to F into Vx, where Vx is the velocity in the direction of force. Now, within a fluid, forces arise due to stresses. Specifically, our source talks about shear stress or momentum flux denoted by pi. The shear stress in x direction, pi x, represents the force exerted in x direction per unit area. Therefore, the force exerted in x direction on the surface element ds is pi x into ds. The rate at which work is done by this force is then pi x into ds into Vx, and the rate at which work done per unit area or the work flux is pi x into Vx. Importantly, we expand on the components of this work flux. For a surface perpendicular to x direction, the work done involves not only the x component of velocity, Vx, and the x components of the stress tensor tau xx, but also the y and z components of velocity, Vy, Vz, interacting within the corresponding shear stress components tau yx, tau zx. Now we'll look at the contribution of energy flux in the x direction due to this work. It can be denoted as tau xx into Vx plus tau yx into Vy plus tau zx into Vz. Similarly, for surfaces perpendicular to y and z, we have analogous terms involving the corresponding stress components and velocity components. These terms represent the rate at which the work is being done by the viscous stresses as layers of the fluid move relative to each other. This work, as well as we'll see later, can contribute to the heating of the fluid. Think about stirring a viscous liquid like honey. You're applying a force, and the different layers of honey move at different speeds. There's a friction between these layers, which is related to the viscous stresses. The work you do in stirring is being transferred through these stresses and ultimately contributes to a slight increase in honey's internal energy, a form of viscous heating. Now let's discuss about conductive heat flux. The third key component of the combined energy flux is the conductive flux or molecular flux denoted by Q. We have various components in x, y and z directions denoted as Qx, Qy and Qz respectively. Conductive heat flux is fundamentally governed by Fourier's law of heat conduction. This law states that heat flux is proportional to negative gradient of temperature. In simpler terms, heat flows from hotter regions to colder regions, and the rate of heat flow is greater for steeper temperature differences. So Qx is directly proportional to minus dou T by dou x, Qy to minus dou T by dou y, and Qz to minus dou T by dou z. Where T is the temperature, the proportionality constant is the thermal conductivity of the fluid. Therefore, the conductive heat flux vector Q represents the rate at which thermal energy is being transported through the fluid due to these molecular interactions driven by temperature differences. Even if the bulk fluid is not moving, heat can still be transferred from a hot part to a cold part through conduction.